Hey guys, today I'm going to start a series of videos from chapter 5. Much of chapter 5 you guys are actually going to read on your own time. Much of the information isn't terribly difficult. I just want to highlight two of the more difficult subjects. So here's the first of the more difficult two. So nuclear chemistry. Nuclear chemistry is where we're going to study radioactivity or radiation. So, what is radioactivity or what is radiation? Radiation is the emission of tiny particles by the nuclei of certain unstable atoms. So, as I alluded to in chapters past, this is going to be one of those cases where we're trying to gain stability. Everything we do in chemistry is about stability. So here we have an unstable atom. It's going to emit some sort of tiny particle, and that's going to help it to gain some stability. When it emits this tiny particle, that is called radiation, the emission of that tiny particle. One of the things that's going to be really important to us this chapter is this symbolic representation of isotopes. So just to remind you guys what this looks like and what it is, let me grab my laser pointer. Here we have the chemical symbol. On the bottom is going to be the atomic number or the number of protons. And up here is the mass number. Remember that mass number is protons plus neutrons. So we're definitely going to see this symbol a lot in this lecture. There's going to be 4 types of radioactive decay or radiation that we talk about. So this is just a summary slide. We're going to have alpha, beta, positron, and gamma. So we'll work through each one of these nice and slow and see how we can follow this process. The first type of decay that we're going to talk about is alpha decay. So there's lots going on this slide, so I want to make sure that I break it down nice and slow for you guys. So an alpha particle, when we have an unstable nucleus and it undergoes alpha decay to gain stability, it's going to emit an alpha particle. So what is an alpha particle? An alpha particle is 2 protons and 2 neutrons. So that's what an alpha particle is. If I were to symbolically represent that alpha particle as an isotope, so 2 protons, that's going to be the number that goes on the bottom. The mass number would be the protons plus the neutrons. So that's the number that goes on the top. And essentially, an alpha particle is a helium atom, right? So somebody that has 2 protons is a helium. So essentially, that's what an alpha particle is. So very often, this is how our alpha particle is depicted. Okay. So here's our unstable nucleus. It emits an alpha particle. One of the unique properties of nuclear chemistry is that after this chemical reaction happens, after this takes place, we actually form a new element. So if we're getting rid of protons, obviously that's going to create a new element for us. And this new element is a more stable element. That's the whole purpose, again, of this exercise. So here is a nuclear equation. So this is something that you guys are going to have to write out for me in the coming homework and quizzes. So here is our original element. So we got uranium-92. This was the unstable element. Uranium is going to emit an alpha particle. So it's going to get rid of 2 protons and 2 neutrons. So here's our alpha particle. The new element that forms, in this case, is going to be thorium. When we write this equation out like this, it has to be balanced. Well, what do I mean by balanced? The number of protons on the left-hand side has to equal the number of protons on the right-hand side. So we started with 92 protons. We have to end with 92. So here's 90 plus 2, so 92 on this side as well. And the mass number has to be the same. So we started with a mass number of 238. And the mass number over here has to equal 238. So 234 plus 4, that would give us 238. So when we write these nuclear equations out, we have to have the same number of particles on either side. So let's look at an example. Here we have an example of an unstable isotope. It is going to undergo alpha decay, so it's going to emit an alpha particle. What is the new stable isotope that forms? So go ahead and pause your video, see if you can figure it out. Then I'll walk you through it. Okay, so to write out this equation, I'm going to go ahead and put my reaction arrow. So this right here is called the reaction arrow. I'm just going to rewrite what they gave me. Okay, so whoopsies. To decide what the new element is, if radium gets rid of 2 protons, so the alpha particle has 2 protons. If radium gets rid of 2 protons, this number is going to go down by a number of 2. So over here, it would now have 86 protons. And if radium gets rid of 4 of its mass number, so 2 protons, 2 neutrons, radium gets rid of 4 of the particles from the mass number. That means this is going to be a mass number of 220. Now we just need to write the chemical symbol. So how in the world am I going to get the chemical symbol? Well, I'm going to get it from right here. I'm going to look at my periodic table. I'm going to see what element has 86 protons. I'm looking at my periodic table. Oops, it's clicking on me. It's going to be Rn. Okay. Now I just need to double check that everything is balanced. So mass number of 224, 220 plus 4, that gives us 224. Number of protons is 88. 86 plus 2 gives me 88. So she's erasing my work and clicking through this slide, we see the same process. All right, so when we talk about each of these different types of decay, we're going to talk about how much damage they do. And then we're also going to talk about how easily they can get into and out of systems. The easiest system to talk about, probably the most interesting system to talk about, is the biological system. So we're going to talk about the ease of them getting in and out of the body, for example. So penetrating power. Penetrating power is going to be the ability of these alpha particles to get into something. So get into our bodies, for example. So for alpha particles are actually pretty large particles in the nuclear chemistry world. So penetrating power of an alpha particle is relatively low. It's hard for it to get into our body. We can block it pretty easily with like a piece of paper or clothing, or just our skin will block it. So penetrating power is low penetrating power. So think about a semi-truck in a traffic jam. It's not going to be able to get in and out very easily. The other thing we're going to talk about is ionizing power. So ionizing power is the ability of that radiation to destroy molecules and atoms. So when these alpha particles come into contact with biological cells, what ability do they have to destroy those cells? With alpha particles being very big particles, their ionizing power is really high. So think semi-truck in an accident. Semi-truck meets car, semi-truck meets motorcycle. Semi-truck's going to win, right? It's nice and big. So penetrating power is low. It's pretty easy to block it from getting into our biological system. Once it enters the biological system, or if it does enter the biological system, it can do lots of damage in there. So here's just the summary slide for alpha decay. So alpha particles are consisted of 2 protons, 2 neutrons. We see the isotope symbol for the alpha particle. It has high ionizing power and low penetrating power. All right, the next type of nuclear decay that we're going to talk about is a beta decay. So in this case, we've got our unstable nucleus here. And when it undergoes beta decay, one of the neutrons is going to transform into a proton. So a neutron's going to become a proton, and it's going to emit an electron. So neutron becomes proton, neutrons are neutral, protons are positive. So the electron just helps us to navigate that charge, the change in charge there. So here's our unstable atom. Here's how we depict a beta particle. So if a neutron becomes a proton, well, of course, the mass number is not going to change, right? A neutron has a mass of 1. Proton has a mass of 1. So by transitioning from a neutron to a proton, the mass doesn't change. And then this -1, you can think of it 2 ways. You can think of it as the electron that gets emitted, or it'll help us when we're balancing that atomic number, that number of protons down there. And then we give the beta particle the symbol E, and that just, again, helps us refer back to this electron that gets emitted. So balancing a beta decay, here is our radioactive isotope. So when this carbon-14 undergoes beta decay, we're going to emit a beta particle. So again, the mass number doesn't change, but the number of protons does change. So if a neutron becomes a proton, what's going to happen to the atomic number here? We had 6 protons. Now we're going to have another one, right? We just formed a new proton. So that atomic number is actually going to go up by 1. So the new isotope is going to have 7 protons. And then again, mass number was 14. Mass number is still 14. No change there. When we go to balance these, so to make sure the number of particles is the same, we have 14, 14, 0. So the mass number stays the same. Here we had 6 protons. We go to the product side. We've got 7 protons minus 1. So 7 minus 1, we get our 6. So that helps us to balance it. All right, so here's another example of beta decay. So again, pause the video and see if you guys can determine what the new isotope is. All right, so here we have berkelium. Berkelium undergoes beta decay. So first thing I'm going to, whoopsies. Oh, goodness. So the first thing I'm going to do is I'm, again, just going to rewrite what they gave me. and our beta particle. All right. So what do we know about beta decay? Well, we know for beta decay, the mass number is not going to change. So I still have 249 up here. In beta decay, remember that a neutron becomes a proton. So if a neutron becomes a proton, this 97 is going to go up to 98. Okay. And then we just need to determine what the new chemical symbol is. So go to your periodic table, find the 98th element, and we see that the 98th element is californium, CF. And then again, making sure everything is balanced, 249 on the left, 249 and 0 on the right. That's good. 97 on the left, and then 98 minus 1, 97 also on the right. So everything is balanced. So clicking through, we see the same process. So berkelium undergoes beta decay to form californium. Any guess where these elements were discovered? Both of them were discovered at Berkeley in California. So just kind of a little fun fact there. All right, so for beta decay, we're going to talk about penetrating power and ionizing power. So for beta decay, penetrating power, think of it as your car or sedan. It's going to have moderate penetrating power. So it's a little bit smaller than the alpha particle. So it can wiggle its way into biological systems a little bit easier. So we'll need some thick clothing maybe to protect ourselves from beta particles. So we have to be a little bit more mindful about what we choose to guard ourselves with. Ionizing power, however, is a moderate ionizing power. So in the event that a beta particle does enter our system, it's only going to moderately destroy molecules and particles in there. So again, think of a sedan or a car in an accident. It's going to do some damage, but not nearly as much as a semi-truck. So moderate penetrating, moderate ionizing. And then again, here's our summary slide. So beta particle, electrons are emitted from a nucleus. A neutron becomes a proton. There's our symbol for a beta particle. Intermediate or moderate ionizing power, intermediate or moderate penetrating power. Right. The next radioactive decay that we're going to talk about is a gamma ray. So gamma rays aren't technically a particle. Gamma rays are electromagnetic radiation, or it's a wave. So gamma rays are just waves that are being emitted. Gamma radiation very often happens in conjunction with something else. So here we see that alpha decay from the first example, and there's also some gamma radiation that gets emitted with that. The gamma radiation is depicted with a 0 and 0 because no particles are given off. It's just a wave. And then this funky Y looking thing is the symbol that we use. So while we don't have to talk about balancing nuclear equations with this, we certainly will talk about penetrating and ionizing power. So gamma, being a wave, it's very, 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 very small compared to the other types that we've talked about. So penetrating power for gamma radiation is really, really high. For gamma radiation, we've got to use things like lead vests or cement, concrete to block gamma radiation. So we have to be very mindful of blocking it to try to stay away from it. So think motorcycle in a traffic jam. That motorcycle can weave in and out pretty quickly. Ionizing power, however, is very low. So while gamma can get into our biological systems pretty easily, it doesn't do a lot of damage when it's in there. So it's got a relatively low ionizing power. So again, think motorcycle in an accident. When that motorcycle hits a car or a semi-truck, it's going to do a little bit of damage, but certainly not a whole lot of damage. Okay. So again, here's our summary slide. Gamma rays are actually electromagnetic radiation, which is the fancy word for it's a wave. Gamma rays are given the symbol right here. And then they have low ionizing power. They don't do a lot of damage. High penetrating power, they get in pretty easily. The last type of nuclear decay that we're going to talk about is the positron decay. So positron is essentially the inverse of beta. So beta, neutron became a proton. In positron decay, a proton becomes a neutron. And what gets emitted is a positron. So a positron is given this symbol E or this kind of beta symbol. You'll see both of them. The mass number, again, doesn't change because we're talking about protons and neutrons. Both of those have a mass of 1. The number of protons does change, however. So if a proton becomes a neutron, that positive charge has to go somewhere, right? We have a positively charged particle. Now we have a neutral particle. So that's where this +1 from the positron comes from, is that change in charge. Okay. So here we see an example. This is a hydrogen isotope. It undergoes positron decay. So the mass number doesn't change. It had a mass number of 1. It still has a mass number of 1. And then there's our 0. However, in this one, the one and only proton for this hydrogen, that proton becomes a neutron. So when we go to the other side, if this proton becomes a neutron, there's a 0 there. And then here's that +1. So we have 1 on the left-hand side, 0 +1 on the right-hand side. So again, we're balanced. So here's an example. Go ahead and pause the video and see if you can decide what the balanced nuclear equation would look like. All right, so potassium undergoes positron decay. So here we see that positron being emitted. So what is the new isotope that gets formed? So again, just rewrite it down here, reaction arrow, and here's my positron. Okay. So what do we know about positron decay? The mass number does not change. So the mass number is still 40. In positron decay, a proton becomes a neutron. So we use up one of these 19 protons. So that number is going to go down to 18. And that's where we see it written over here. So look at our periodic table. We find the element that has 18 protons, and that element is argon. Again, just making sure everything is balanced. We have a mass number of 40 on the left-hand side, mass number of 40 plus 0, that's balanced. And then a atomic number of 19 over here, and then on the right-hand side, 18 plus 1. So that gives us 19. Go back to the pen here so I can erase. And as I click ahead in this slideshow, just again, the same process that I walked you through. I don't have a slide for positron decay as far as penetrating and ionizing power. But if you think of it as the inverse of beta, what that tells you is that positron particles are essentially the same size as beta particles. So positron would have a moderate or intermediate penetrating power, moderate, intermediate ionizing power. So again, this is going to be an example of like a sedan or a car in our analogy. So here's just a table from your textbook. This does a great job of just summarizing alpha particle, symbol, what it changes, and then the mass number and the charge change there. Okay. So that's where this section of the lecture is going to end. In the next lecture, I'm going to talk more about half-life reactions.